Okay, welcome everyone. Welcome to the spring version of the Zurich Distinguished Visitor Program on climate change. This endowed program is really important to the Bren School and allows us to attract international leaders in policy and law and science of climate change and bring them in for colloquia such as this, but also to participate much more broadly in the educational program at the Bren School, and it's really had a major impact on our program here and issues related to climate change. But before I introduce our speaker today, I want to recognize a guest who's representing Zurich Financial Services. Today we have David Sellers-Smith here with us. David is from the Farmers Group, and he's the government affairs coordinator there and works on a wide range of public policy and environmental issues for the company. And we appreciate the really strong interaction that we have with the whole Zurich Financial Services team, and appreciate David being here today. So our speaker today is Don Wuebbles. Don is the Harry Preble Professor of Atmospheric Science at the University of Illinois. He's an expert in numerical modeling of atmospheric physics and chemistry, and he's been a lead author on several national and international assessments on issues related to climate change. These have won many awards. He and his colleagues, for example, shared the 2005 stratospheric...
Oh, sorry.
Huh?
I'm looking at the wrong time.
Oh, sorry. 2007. Well, no, the 2005 Stratospheric Ozone Protection Award,
yeah,
and the 2007 Nobel Peace Prize for his work on the IPCC. He's now a lead author for the next version of the IPCC. I'm sure he'll have some fun stories to tell us about the interactions that all brings in with a variety of people that strongly believe in the science that he does. And his work has been very important in terms of moving forward our understanding about the physical and chemical nature of atmospheric responses to climate change. So today he's going to talk on severe weather in the U.S. under a changing climate. Don.
Thank you all. It's very nice to be here. So what I'm going to do is kind of focus on some of our findings from the U.S. National Climate Assessment, and particularly focusing in on the severe weather aspects of that, because the media likes to talk about global warming. The science community is, for essentially all the time I've been working on this, which seems like forever, I've really called this climate change, and there's a lot of people out there confused about that, but the reason we did that is because we knew that it was a lot more than just a little change in the temperature, which could sound very comforting, to just call it global warming. It's really more like global weirding that has also been used in the press. So I'm one of the leaders in the U.S. National Climate Assessment, and this all basically started in 1990 with a bill in Congress called the Global Change Research Act, which was to put in place that every 4 years there should be a special report that analyzes the effect of global change, particularly climate change, and its effects on the natural environment and all the potential impacts that might mean to society in the U.S., plus ecosystems, et cetera. And after that bill was signed, it was immediately forgotten. Finally, in 1998, when the government was under pressure to actually put out something, they did call for the first assessment, and that came out in the year 2000. And I was involved in that, although not to the extent I've been involved in the last two. It was done very, very rapidly at that time. It used basically two climate models, and I think that was the big problem with it, is that it really used some very early results and didn't look at broadly enough across what was going on in the community to really look at. But the basic conclusions were the same as the conclusions we're making now. So after the 2000 assessment, the act was kind of forgotten again until George W. Bush was actually being sued in 2008 to why wasn't there another assessment. And so at that point, through the White House, a small panel of 32 or 3 of us was put together to do that assessment. And we came up with we purposely tried to keep it to originally less than 100 pages, ended up being around 150 pages, and written for public reading. So all the science jargon was taken out of it. We used American units, which really bothers people in the sciences. Why would we do that? But it is much more readable for Americans. So that came out. That was supposed to come out actually right around the time of the election in 2008, and we had it ready to go, essentially. And we had to make some revisions after that, but only after the White House told us that no, they did not want to see it then. They thought it should go through another review process. And as a result, it actually came out in June of 2009, and we released it at the White House. The idea was that these should be done every 4 years, and so now we are trying to do it every 4 years, and so we started this process the last year with the aim of finishing this year with the new assessment. I don't think we're going to quite make that. I think the public release will be something like March of 2014, but it will come out. So the way it started was first by forming a 60-member Federal Advisory Committee. If you've ever been on one of those kind of committees, it is a very involved process to participate. It's not the way things should function, but it's the way it does. But nonetheless, we made it work, and we formed an executive secretariat, which is 13 of us, that essentially really leads the process, and we use the Federal Advisory Committee to approve what we're trying to do. That led to the formation of the report, and it is an ongoing process. We just went through the public review and a special NRC review, National Academy review, and I'll say a little bit more about that in a few minutes. The actual report has 62 authors. By the way, all of these different committees really truly represent America, because it's not just academics or government people. It also we also have people from industry, variety of different sectors, non-NGOs or non-government organizations, and variety of different organizations, including American Indian tribes. So it really does look like our country. We have 62 convening lead authors, 180 lead authors for the 30 chapters that represents assessment. We're going to try to go through those 30 chapters as part of the class I'm going to do over the next week. It sounds daunting, but most of it is very, very easy reading, and the graphics take up a lot of the space, and so I'm hoping that we can do that effectively. We'll find out, but I'm hoping so. So I was in charge of the chapter on the science of climate change, plus 2 appendices, one that further expanded on that because we didn't think we had enough space in the actual chapter. The original idea was to keep each of the chapters very short. So the appendix gives you more information, and then I also had this bright idea, which then led to a lot of work, that we should try to do a commonly asked questions chapter as well. Or actually, originally I was thinking of that as being a separate report, but now it's been turned into one of the appendices. So the outline, going beyond what I led, which is a scientific basis for climate change, we next go into the sectors like agriculture, water, transportation, et cetera, that where climate is likely to have great impacts. Then cross-cuts across a number of those because they don't all fall into easily discussed narrow aspects. Then we look at a regional analysis because people care about climate where they live, and so we broke the country into 8 different different regions, and those different regions then are discussed in separate chapters. Then we look at things like decision support and various policy questions, and finally, we want to turn this into a process that could be accomplished every 4 years. Hopefully without driving the science community crazy as we try to accomplish that. We did complete the public review on April 12th, and now we're in the process of revising the chapters, responding to the 4,000 comments we got from the public and from the NRC and from agencies. And that will put us up to June of 2013. I have to turn in my chapter by early June, and then there'll be review editors that have been selected for each chapter that will then go through each of the responses to the comments to make sure those were adequately done. We'll continue to revise the chapters over the summer, making improvements in graphics and so forth, such that by early fall, we'll then do a second NRC review. I think the governments probably will see, different agencies will also see it at that time. And then we'll go through finally a White House review just before it comes out. And then we hope to have it out officially by, it'll be at Congress's hands by the end of the year, but the official public announcement will probably be more like in March 2014. Well, if you go back and look at the last assessment, there's a lot of key things that we discussed in terms of what's being observed about climate change. It's not just the increasing temperature, but the increasing amount of precipitation coming as intense downpours, rising sea levels, retreating glaciers, thawing permafrost in Alaska, longer growing season throughout the entire country, more so here in the West actually than in the East. Longer growing season, as mentioned, longer ice-free season in oceans and lakes and rivers, particularly seeing that in the Arctic. Earlier snowmelt, changes in river flows, and on and on and on. Well, I can tell you basically the new assessment says more or less the same things. But we're going to go look at some of those in more detail. As part of getting the assessment going, I and some of my colleagues ran a series of 4 workshops that looked specifically at questions about extreme events and what we know about those relative to climate change and what we don't know. And that has resulted in 4 papers for the Bulletin of the American Meteorological Society. The first one actually just appeared this month, the issue that just came out very recently. And the other 3 will be coming in the coming months. It takes a long time for them to seem to publish these documents. This graphic is aimed at trying to pull together what we learned from those 4 workshops to say, well, what can we say about detection of these severe events relative to climate change, and how well do we understand the causes of those the changes that can occur. And there's some things, oops, I just goofed, floods, precipitation, heat waves, cold waves, floods, and droughts, we have pretty strong knowledge about. And those are probably the things we can spend some time talking about. I hope this is clearer back there than it is up here, but there's some areas such as hail and tornadoes, ice storms, things like that, where we really don't have sufficient knowledge to be able to talk about trends and the causes, how those things might change with the changing climate. Hopefully our information on those will change over the coming decade. But and there's some are kind of in the middle. Some things we can say some things about hurricanes, and there's other things we can't say, for example. So what I'm going to do is mostly concentrate on that upper right corner to talk about things like extreme temperatures, heat and cold waves, extreme precipitation events, floods, droughts, and extreme storms. Start out with extreme temperatures. First, let's take a look at the global understanding. And as we look at changing trends, what kind of things might we see? Well, we might see an increase in the mean. Certainly have seen that, as you'll see shortly. Increase in the variance. Not so sure that we have seen much there. And a possible increase in both. But the tendency is that you're still going to have cold events, but just not as many as before, and perhaps a lot more hot extreme events. And if you then look at the temperature record, this is from a study by Jim Hansen and others at NASA GISS. This looks at the analysis of the global temperatures, which really has pretty much of a Gaussian type shape, relative to first the period 1951 to 1980, and it just looks at the last 3 decades, what's been happening. And then what you see is it really has been a significant shift with much more tendency towards large standard deviation events. The very, very unusual events are becoming much, much more common, of very high temperature days. So this is done in terms of looking at in terms of relative standard deviation. I'm going to assume that everyone here knows what that means, and if you don't, please ask. You can look at this further by just looking at the maps of global temperature. This is 1955, 1965, 1975, during that first period, and you don't see many situations of really large 2 sigma, 3 sigma events. Whereas you look at the last, this is 2003, year by year up through 2011, you see very significant increases relative to that earlier period in terms of severe events. That doesn't mean it's this, you're going to necessarily get large temperatures everywhere, or that you're getting large temperatures all the time in certain locations, but overall, globally, we're seeing a very significant change in temperature. Well, one of the aspects in the U.S., the new U.S. assessment that is different than the 2009 assessment was that we have a much better analysis of all the different weather station data than we had previously. The NOAA National Climate Data Center essentially went through all the records going back to 1900 and before, but particularly 1900 when we had really thought we had a national network, and have tried to very carefully look at each measurement and essentially correct for anything that was a potential issue, including the fact that there's been changes in not only instrumentation, but in the times of day in which measurements are made, and so on and so forth. So those kind of shifts all have an effect, and you need to account for those kind of biases. So that's all accounted for in the new studies. Now, did it change the basic conclusions? Not at all. But what it did do is just give us more confidence in what we're doing. This is the observed temperature record itself. This is for the U.S. I I think this is just for the contiguous U.S. And basically, we've seen about a 1.5 degree Fahrenheit increase in temperature. I'm going to try to mostly use American units in this because that was the graphics we've been using for the assessment. There may be a few slides that are exceptions to that. So the overall, we've seen a significant change, and much like we see in the global temperature records, we see an increase from about 1900 to 1940, kind of a leveling out from 1940 to 1970. That is probably related to two factors. One is increased amount of coal burning that increased the amount of sulfates in the atmosphere, but the other is ocean cycles and the influence of natural variability. And then since 1970, we've seen a very significant increase in temperature, both in the US and globally. If you look at the trends for 1960 to 2009, you see essentially all parts of the US have seen an increase, the red indicating an increase, and the size of those circles indicating how much of an increase. If you looked at it compared to the recent period relative to the earlier period, there's some periods where some locations where you actually see a very slight cooling, particularly in the southeast, which is called the warming hole. But over this last 50-year period, that's not been the case. This graphic actually tries to then look at a little bit more detail. I mentioned the 8 regions. This breaks it down by the different regions and the kind of temperature changes we've seen per decade. The overall change for the period of 1991 to 2011 relative to the first half part of the century, we chose 1901 to 1960, with 1960 kind of being a breaking point in a lot of the observations, so it became a good place to kind of do everything relative to. And you see particularly this, you see this kind of warming hole, but much of the country is seeing very significant warming in these last few decades. If we turn to the southwest, and the southwest region, of course, not only includes California, but also includes Arizona, New Mexico, and I think it was Nevada as well. We see an increase in all seasons, leading up to a global change or a change over the region that looks much like what we saw nationally. The growing season I mentioned is lengthening. This is the number of days in each of the regions. The West has seen an increase in by 21 days, 3 weeks. Again, this is 1991 to 2011 relative to 1901 to 1960. But all parts of the U.S. have seen an increase in the growing season. One of the ways of looking at whether our climate is changing is how many records are we breaking, both cold records versus heat records. And one of the things we've seen, if there wasn't much going on, you really should expect it should be 1 to 1. More recently, last few decades, that's not been the case at all. It's about 2 to 1 in favor of heat records during the decade of 2000 to 2009. And 2011, or I'm sorry, it was 2001 to 2010. And then 2011 was 3 to 1 in favor of heat records. And 2012 was 10 to 1. I haven't seen these numbers yet for this year. I guess there hasn't been a lot of records broken because it's been fairly mild and cool. If we turn to heat waves, again, these are all based on observations. The last 3 to 5 decades, we've seen an increase in heat waves in the U.S., particularly in the western states. But overall in the U.S., no real trend, but certainly we've seen a trend in the western states. But less cold waves everywhere. So we're just not getting those cold events as we used to in the past, but we're getting many more heat waves. And these are for 3-day heat wave events. So statistics change a little bit depending on how long you consider a heat wave. For the Southwest, the trends in heat waves has definitely been an increase over this, particularly over the last 50 years. We could also go back and talk about the 1930s and the special events that happened then, but that was a relatively short period of time and didn't have much effect on the long-term trend as you saw in the other graphics. If you look at precipitation, there's been a small increase in precipitation nationally, particularly in the Midwest, parts of the Great Plains and the Northeast. Even in California, there's been overall a slight increase. But we also see large patterns in some locations for decreasing trend of precipitation. More important, though, is heavy precipitation. When it does rain, what's the precipitation patterns look like compared to the past? And basically, we're seeing an increase in large precipitation. This graphic looks at the top 1% of the precipitation in a region in its trend over the last 50 years. And we see really large trends in the Midwest and the Northeast of an increase, but all parts of the country show some increase. So even in the very dry Southwest areas, when they do get rainfall, we're tending to see larger rainfall. That's not surprising given the physics of the climate system. Clausius-Clapeyron equation basically says that as the temperature warms, you would expect that the atmosphere can hold more water vapor. And so there's more water vapor available when you do get the right kind of synoptic system to then get rainfall or snowfall. So this could apply to snowfall as well as rain. Even in some areas like Hawaii, where we've overall seen a decrease in precipitation, we still find that overall there's an increase in the amount of rainfall coming as larger events when it does happen. This looks at extreme precipitation across the U.S. in a different way. This is analysis done by one of my undergraduate students, actually, that looks at a one-year storm, the 5-year storm, and the 20-year storm. And if I were to do this for the Midwest, I don't know exactly what the number is across the U.S., but for the Midwest, that would be about 4.5, 5 inches of rainfall. And what it says is for each of these, even for the extremely unusual storms, that we're seeing a much higher incidence of those storms, such that what was the 20-year storm is now more like the 13-year storm. So it really has changed. That has dramatic effects on engineering related to water treatment plants and reservoir development and so on and so forth. Some parts of the country have seen a significant increase in the amount of floods. This is, and others haven't. This is from an analysis by the USGS, by Hirsch and others from a few years ago. And this map basically shows it in the Midwest and Northeast. We're generally finding a significant increase in the amount of flooding. And the Southwest, basically a decrease, going along with the decrease in precipitation overall in some areas. In other areas like the Northwest and the Southeast, really can't say much. And one of the things from that study, Bob Hirsch and others did, was that the interpretation is greatly affected by human factors such as the building of dams and so forth that have really affected some parts of the country. If we look at droughts, we don't really have a good enough index for droughts at this point. We're kind of stuck right now with the Palmer Hydrological Drought Index, or the Palmer, various versions of the Palmer Index. And there's some limitations to it, but nonetheless, the Palmer Drought Index does indicate that generally the West has been seeing more incidences, more likelihood for drought, and the Southeast as well. Whereas the Midwest and Northeast have generally seen, through that increase in precipitation, overall less likelihood of droughts. Although tell that to the farmers last year, throughout the Midwest, and particularly in Illinois, when we had one of the most severe droughts we've ever had. I used to say that, people always ask me, well, when is it going to take for Congress to do something about climate change? And I always said, well, when we get something that happens badly enough, some event that would really get their attention, such as a major drought in the Midwest that kills all their crops. Well, we had that happen last year and it had no effect. So maybe it's going to take multiple of those events. I don't know. Since 1980, the NOAA has been tracking what are called the billion-dollar events, those events that have a major impact on the U.S. economy. And that includes hurricanes, but it also includes droughts and floods and forest fires and many other events that are all related to weather and climate. And generally what we're seeing, if you look at this, is that in the blue indicating the number of such events, the line indicates the dollar amount. So Katrina, of course, has a big impact for a single year. But overall, we've been seeing an increasing trend in terms of the number of such events. There were 14 such events in 2011, 11 such events in 2012, including several major storms. Costs during 2012, the last I heard, was something over $60 billion, but never heard the exact number. It was $60 billion in 2011. And so one of the comments I got from one of the hurricane experts when I've shown this is that, well, the problem is that people have been moving to the coast and the hurricanes have that effect. And so it's just dominated by hurricanes. So I asked the folks at NOAA who did this to give me the same graph without hurricanes, and they did that. I don't have it in quite this representation, so I'm not going to show it. I can show it individually, compare the two. And you get the same conclusion. Basically, that we're seeing more and more large-scale events that are having a significant impact on the economy of our country, and we should be aware of that. And so climate is having an impact already. We just don't seem to recognize that always. Well, there's been many different analyses now that looks at looking at the attribution of major events and whether there is a detectable human influence. While we cannot basically say, oh, that event is clearly related to human influence, we just can't do that. What we can say is the probability has really changed because of the fact that the background climate has changed the way it has. And so there's been a number of analyses now that have looked at that and have concluded that there was an increased probability, including the European heat wave of 2003, where we had 20,000 deaths in Europe as a result of an unusually hot summer. The Moscow heat wave in 2010, and the 2011 drought in Texas and Oklahoma, which has been found to be about 3 times more likely because of the fact we've changed the background climate. Now, if we look at the future projections, we expect that the kind of trends we've been seeing will continue into the future. This looks like analyses of different scenarios. What are called the ESRA scenarios, A1 or B1, A1B, A2, there's a number of them, where the scenarios that were used in the 2007 and 2001 IPCC climate assessments. The more recent scenarios take a little bit different track. These are the RCP scenarios. These are the ones that now appear in the new IPCC assessment. They start out with a basic assumption of what kind of forcing do you want in the climate, and then back into what emissions you would have to get that reasonable. They're very similar in many ways. They're not exactly the same, of course. And so the high scenarios like A2 and RCP 8.5 give very similar, very large effects, and basically both assume that we will continue to heavily use fossil fuels throughout this century. whereas others like B1 and RCP 4.5, which are also very similar to each other, basically assume by mid-century we start to very rapidly move away from fossil fuel use. There's also, in the new scenarios, RCP 2.6, which would give a much, much lower climate change. I think it's basically unrealistic. I don't think there's any way we're going to possibly reduce emissions sufficiently for that to happen. But it's there to show what impact you could have if you really had a major change in worldwide policy relating to emissions. Looking at these scenarios, this is for the B1 and A2 scenarios across the US. And this is, I think, didn't label it here. I think this is the end of century relative to the last 30 years. We're talking about 4 or 5 degree Fahrenheit increases in the low case, whereas in the high case we're talking about 10 degrees or more, depending on where you live. But very, very major changes in climate in both cases, but particularly if we continue that high emissions approach. These are from the regional climate models. I won't have time to really discuss some of the issues associated with them, but they do give some aspects of what they do, and particularly in temperature, is pretty reasonable. This is the number of days greater than 95 degrees, and much of the country would be expected to see a significant increase in the number of days by the end of by mid-century. This is from mid-century, in the number of days for this scenario, which I think was A2. Yes. So, significant changes in the climate. If we look at the number of days less than 32 degrees, less than freezing, also a very significant decrease in the number of such days, particularly in the West. Less days resulting in snow in the Sierras, for example. We look at precipitation patterns in more general sense. This is an analysis we did for the assessment. This is that very, very low scenario, and this is the RCP 8.5 scenario. So these are based off the new, what are called CMIP5 models, the newest modeling analyses that are going into the IPCC assessment. Basically, all the scenarios give the same basic character, that we essentially expect a subtropic drying. You're going to see that in a bit in terms of when I show you a global map, and a wetter mid-latitudes generally. So if you look at the high scenario, and then there's an area in between. So you get areas like the northwest or northeast and the midwest. We generally expect an increase of precipitation in the winter and spring, a drier summer, not so great for farming. They have those two combinations, harder to get plants in the field, and then in the summer, more likelihood for a drought in between when you get a large rainstorm. And the falls may be roughly about the way they are now. Whereas if you look at the southwest, we essentially find drying most seasons. The only exception being there's latest results tend to indicate maybe a slight increase in the monsoon period in June. But overall, drying in the southwest. So people are already having water problems, likely to have even larger water issues in the future. Just to give you an idea, I don't have this for any of the states in the West. About 15 years ago, I was trying to come up with, one of my colleagues and I were trying to come up with a way of how can we communicate climate change to make it clear to people who didn't seem to be getting it. And so we did what was called the Migrating States. How would Illinois look, for example, as you go through the century in terms of the relative climate compared to other parts of the country? And what we found was that by the end of the century, with the high scenario, Illinois was looking like eastern Texas. Latest map actually is a little more central Texas, but in any case, not too much difference in precipitation overall, where we have now, but much, much warmer. Summers that are essentially above 90 degrees most days. A month that's above 100 degrees. Well, that's not Illinois. And when I showed this to Senator Durbin, of Illinois. He was shocked by it, and he proceeded to show it before Congress, before the Senate several different times since then. Because people do seem to get this. You know, as hard as it is to explain climate change to people, they get this graphic, that Texas is really different than Illinois. And this is for summer. Now, if I showed them winter, because I've had people say, well, gee, I always wanted to spend winter in Texas, you know, doesn't get as much snow. And I said, well, that's not what we're talking about. This is summer. It's when you don't want to be in Texas. Summer is probably, or winter is probably a little bit more like central Pennsylvania. A little warmer than we get in Illinois, but roughly the same amount of snow. So you're not going to escape the snow, but your summers are going to be really miserable. And sometimes they're already miserable. Well, if we look at precipitation, remember I showed you the severe precipitation increase we observed. This is for the U.S., continental U.S. And so this just shows the models relative to those observed, and generally they do a reasonable job, or the models have a much larger variability than actually is found. But generally they expect this is going to continue. So one of the higher scenarios, like A2 or RCP 8.5, we expect that more, we're going to get a whole lot more of the precipitation coming as larger events. But even in the low scenario, that is the case. More precipitation coming as larger events than even we have now. And so more likelihood of flooding, and in between that flooding, maybe more likelihood of drought. Well, if I look at the Southwest, it's this very same conclusion, that we're going to get the high scenario, actually not as much difference between the low scenario and the high scenario, but generally more precipitation when it does coming as a larger event. Another way of looking at this is a map that was just drawn in the last week that we're trying to figure out how we're going to incorporate it in the National Climate Assessment. This is actually something that's going to IPCC that I probably shouldn't be showing. But this shows the maximum 5-day precipitation. And generally, essentially the entire world is likely to see, when you get a 5-day precipitation event, that there will be an increase in incidence of such events. On the contrast, if we look at consecutive dry days, this is the number of dry days, we see this subtropical drying in the wetter northern latitude regions, where we're going to have more days overall throughout much of the U.S. With consecutive dry days. So more likelihood for a mini drought, even if not a major drought, throughout the U.S. compared to what we've had previously. This is also, this is a paper by Weiner et al. From a couple years ago, looking at that Palmer Drought Index, and it also concluded, based on best modeling studies available then, that you would likely see a significant increase in drought throughout much of the U.S. So similar kind of conclusion based on a different type of analysis. Well, I mentioned hurricanes early on. We can't say too much about the West. The Western hurricanes or tropical storms, typhoons are not, do not have as clear a message as we have for the Atlantic. But for the Atlantic, we definitely have seen an increase in the power dissipation index, indicating that we've seen an increase in the amount of intensity overall in hurricanes over the last 30 years, 30 plus years. And that if we look at the model projections, which are shown here on the right, we would expect that that is likely to continue, that more hurricanes, when they come, are likely going to be bigger storms. We also looked at sea level rise. The best analysis we have right now for sea level rise is 1 to 4 feet over this century. But we can't throw out for sure as much as 6 feet or 2 meters. And we wait, new analysis. But the best analysis we have right now from the top oceanographers is 1 to 4 feet over this century. So in conclusion, of the science at least, the U.S. climate is changing. It's changing rapidly. And the scientific evidence shows this is mostly a result of human activities. Certain types of extreme weather events are becoming more common. Trends are likely to continue. You see that in precipitation particularly, but also in heat waves, cold waves, risk of floods in some regions, particularly the Northeast and Midwest, droughts increasing in some regions, particularly the Southwest and Southeast, and an increasing intensity of Atlantic hurricanes also is happening and maybe is likely. The bottom line is all weather today is happening in the background of a changed climate. This is a statement I made at a meeting that got me in deep water with some of the denialist groups. I was their hitman for the next day. But I stand behind it because that's what the science shows us. If we look more generally at what does this tell us about emission patterns in the US in relationship to that, we are seeing the amount of energy per GDP and the amount of CO2 per energy unit decreasing, particularly as we switch from coal to methane throughout much of the country. On the other hand, because population increase, CO2 emissions continue to increase at this point, and we expect it to continue to increase. When it comes down to it, and this is a slide that has not been converted to Fahrenheit yet, it's all about risk. What kind of risk are we willing to take in the future as we look at different levels of potential climate change? And certainly the risk increased greatly as we go through the century. And we're already seeing changes now that are having a significant effect on the US economy. How much longer are we willing to let those continue to increase? I'll stop there and be happy to address any of your questions. Move around a little bit so we can get out of that line.
At this stage here, from a modeling perspective, when you look at projections, what's the area that you feel that still has the most uncertainty?
In terms of the projections themselves? Well, I think that it's a difficult question to answer. There's a number of aspects to it. I mean, certainly in terms of our basic modeling of climate, I think clouds remain the single most uncertain thing, and particularly the interactions between aerosols and clouds, that microscale processes that affect that is a big factor. But there's some other things. We don't do a great job in treating ice. In many respects, if you look at many of the models, they really underrepresent the observed changes. And so it's not like the models are over-predicting, they're under-predicting. And that's certainly true in the Arctic. The models are way under-predicting how much ice decrease we've already seen in terms of sea ice. But it's also true for Greenland and land ice as well. And so I think the improvements we're making over this next few years in those aspects, longer term, perhaps in the clouds, although the cloud models are improving all the time, I think are going to be the things that really make the big difference. Yes?
So in case you remember data that the teams working with, what were one or two of the initial results that you're finalizing now that you personally found most surprising?
I think that probably the most surprising part for me was this increase in intensity. I think we already knew from the 2009 assessment that there was an increase in the amount of precipitation coming in larger events, but we had not done the analyses at that time to say, well, how is this likely to continue to change, or to quite look at it in detail across the US in the way we have this time. And that really kind of surprised me. And in fact, that increase in intensity is really being seen worldwide. That's going to be one of the findings in the new IPCC assessment. But it was really dramatic that we're seeing that. Some things like heat waves I can expect it to occur, cold waves, things like that. But the intensity of precipitation really did affect me. It didn't surprise me in some respect, but certainly in the Midwest. I don't know how many 100-year or multi-100-year storms I've heard about now in the last 20 years. It seems, or floods, I mean, flood events occurring. It just seems like there's almost one every year. And it's not quite that bad. There's been 4 or 5 of them, though, in the last 20 years. And, you know, at some point we've got to say, well, what was a 100-year storm really isn't a 100-year storm anymore. So we're trying to take a closer look at those kind of questions. Yeah.
It's really, I was comparing the U.S. temperature record with the global, just from recollection. One thing that really struck me is that there's a big jump in, I think, about 98, 99 in the U.S. record. It was almost like 2 Fahrenheit warming. I assume that's attributable to the El Nino, the big El Nino at 98.
98, yeah, 98 really has an influence if you just look at the graphic, because the lines we put through, we average over that.
The U.S. record than in the global. I just wondered if you could comment on that, and also just whether your assessment looked at ENSO in terms of its influences on U.S. climate specifically.
Yeah, you know, there's a lot of uncertainty about the effects of ENSO, El Nino, and La Nina events still, but nonetheless, yeah, we actually have a subsection that looks at that question. There is no question that El Nino and La Nina events do have an effect on U.S. weather. You know, clearly a cooling effect when there's a La Nina, clearly a warming effect when there's an El Nino. But it's not 100% understood exactly what all those teleconnections are yet, and how to account for that if you were to try to look at climate projection. Yes?
In the slide of the process by which the assessment gets produced, there's a place where there's expert review and public review, which seems like maybe a way polarized extreme. I'm interested if you could characterize what the public review comments tend to look like.
Well, it was kind of all over the place. There was one, you know, if the Cato Institute actually announced their review and listed as 135 pages of review. I don't think when it got translated to us it was anywhere close to that. I don't know if they were using, you know, I don't know how they expanded it into that, but on their website they announced it as 135 pages or something like that of review comments. They did have some pretty nasty review comments about how biased we were, et cetera, et cetera. A lot of very detailed comments about specific aspects like climate sensitivity, the hiatus in temperature over the last decade, some things like that we're putting in extra information about to specifically respond to those in the chapter. That'll actually make the chapter better, I think, because it'll explain some of those things better to the public than we had before. The things that their approach was, though, well, climate sensitivity is 40% lower than even the accepted record by IPCC, based on this one recent paper, or a couple recent papers. And we said, no, you know, actually I just wrote that section a couple days ago. And you know, if you look at all the recent papers, they still have the entire range we had before for climate sensitivity. The canonical experiment there is a doubling of the amount of CO2, and it gives you roughly 1.5 to 4.5 degree centigrade increase in temperature. And so we're sticking with that range. You know, there's no reason not to. In fact, there's some recent analyses that suggest the higher end of the range may actually be best. So I had to respond to some of those things. So some of the comments were actually very useful to us because and other ones were just nasty. And some of the other public comments were kind of nasty. Mostly overall, though, I would say 90% of the comments we got were very useful. They tended to say, you know, this wasn't clear to me. So it made us think about, well, what was the wording about? So things like that. Yes.
You showed an image of the globe with consecutive dry days, and what struck me about that was that North Africa, South Africa, and Australia were vibrant deep red. You said the U.S., not too much big change, not a lot of huge impact here, but those other areas of the world
no question.
looked devastating.
If I wasn't concentrating on the U.S. assessment, I would have said more about those.
Would you say a few more words about what you think those impacts are going to be?
Well, I can give you a personal example for Australia. We had our last IPCC meeting in Hobart, Tasmania, just island south of Australia, which is part of Australia. On the and all during that week-long period, they were having, this is in January, having terrible problems with fires, bushfires, as they call it. They don't have trees or forests, so they don't have forest fires, but they have bushfires, and because it already is pretty dry country, right? On the way home on that Saturday, I had to go through Sydney. Sydney sits on the coast. It was 125 degrees in Sydney that day. I couldn't believe that, you know, here's a place sitting right on the ocean. It was 125 degrees. I think it's a flavor of things to come. Australia is going to be a very difficult place to live, I think, in the coming decades. And parts of Africa are going to be much the same way. But I also tend to think that, because I'm kind of biased, I think, living where I live, I tend to think Phoenix is almost like that. You know, you can't go outside in the middle of the day now. What's it going to be like in another decade or so?
Do you think that this will result in displacement of people from places like
There certainly has been serious questions about that, and there's even some talk of displacement in the U.S. as we melt the permafrost in Alaska, for example, that some towns are going to have to be moved because the towns are just going to crumble. So so I think displacement is a potential real problem. And if you talk to Department of Defense, they're certainly concerned in looking at national security about how climate change may affect our national security over the century because of what it's going to mean to different borders in different countries. Yes?
I think that just the last slide we mentioned these priority areas, agriculture was right up here at the top, and looking at your superimposition of Illinois down to eastern Texas, grow corns would be eastern Texas. So
Actually, they do.
yeah.
You know, just not with, they do, they grow both, but they don't, the yields aren't as good. And so you can still grow, and what the companies like Monsanto are doing are trying to genetically change the crop so it can more adapt to more drought conditions, for example. And so they think that, you know, they'll be able to keep going. But you got to figure that there's probably going to be some impacts because it's not only the change in temperature I was showing there, and change in temperature precipitation, but it ends up, for example, the increasing amount of CO2 that insects, you know, we already know plants like increased CO2, but weeds love it even better. So you get more problems with weeds. Insects love high CO2. We don't fully understand the physiology there, at least from what I've seen. One of my colleagues in one of our other biology departments wrote a paper last year in Science about that they found that with some plots, special plots we have near the university, that increased CO2 resulted in a huge increase in the amount of insects. So you got more insect problems, more weed problems, more likelihood of vector disease problems, and on top of that you got the floods and droughts issues to deal with. All those additional stresses, I think, are likely to have a negative impact on agriculture over the century. Over the next decade or two, I'm not sure we'll see much impact. But over long term, I think definitely an impact. And that's when I talk to farmers, that's the kind of thing I tell them. Yes? That's good. Yes?
So I have a question about methane. And it seems like there's some renewed debate about sort of the atmospheric physics involving methane and its ability to trap heat. So how is the IPCC specifically dealing with that?
I guess I haven't seen what you're talking about, but as far as I know, the molecular absorption is known fairly well, and that I don't think there's a major change in the radiative forcing from that.
I guess the debate is over time scale in terms of its global warming potential at a given time per kilogram.
That shouldn't be, when we did IPCC 1990, and I was one of the coordinating lead authors of the chapter that was in charge of the biogeochemistry and the radiative forcing. We did that first analysis of it. I also led the development of the GWP concept. So I don't really expect there to be a major change. We have known for some time, and maybe some of the analyses haven't accounted for this, that the response time for methane is much longer than its lifetime. And that's because of the fact that when you change methane, it affects the amount of hydroxyl, and you've got to account for that. But if you do, then, and that would affect shorter GWPs. I don't think 100-year GWP, it might have some small effect on. I don't think it would have a major effect on. That might be what you're talking about.
Are you talking about the permafrost release?
No.
No, these are some of GWPs. Yeah.
Okay, one last question.
So I get two.
Did I get students ask any?
Yeah.
Oh, you're a student. Yeah, good.
Let me ask you about the Midwest drought. Because I was fascinated by the fact that in the projections you showed, I don't think, it wasn't a strong indication there would be more droughts in the Midwest, but that event, had a huge impact, and most people saw it as kind of part of the climate change package. So I just wonder how do you see that? In other words, is that drought event something we should see as part of the anthropogenic impact, or is it something different in the sense that it's not really part of the overall projection?
Yeah. First analysis of that particular drought just came out by some analysis by Horling et al. Out of NOAA and Boulder that indicate that, and I think there's several other papers now backing it up, that there's no signs of an anthropogenic impact. They can't do an attribution study relative to that because it just is not a clear signal that you can explain that one purely through the natural variability. We would expect, I did a little bit of analysis on that myself, we would expect probably over the next 25 years that we'll see another such drought, even through natural variability, that just accounting for the state of the ocean cycles and where they're likely to be is likely to result in another major drought. But in the long run, could there be an anthropogenic component to drought in the Midwest? I think definitely, just from the suggestion that we expect to have more dry days in between major storms, particularly in summer, could lead to mini droughts that would have, certainly have some impact on crop production. Okay.